expectation, and similar kind of conditional expectation will also come in the case of what we call it continuous random variable. So right now fully we are discussing about discrete random variable. So things are with perspective of discrete random variable. And discrete random variable in sense why it is very much useful is that whenever you are taking data, then all data is always we are talking about finite number of data points. It is not like that continuum of value. We are having finite number of data points. That means automatically we are having a discrete fashion there in the sampling. So that's why it is very much essential to understand a discrete random variable completely. And continuous is what? From continuous we can always apply discretization, and through that you can always do whatever you want to do with continuous model. That one course you might have already gone in math 2, there is one numerical method, so you might be already aware of that, how you can approach that continuous model. If you are having a continuous model, just apply this some kind of numerical scheme, numerical technique in order to convert that continuous model into discrete model, and just proceed with that, because discrete model is what it is, a practical approach to deal with any kind of problem. So that's why you are having a very good computational approach to deal with the discrete model. And you might be aware of that, you all are from CSE, so discrete structure is only meant to proceed with the computation in the computer is always dealing with discrete structure. That's why you might have one course on discrete mathematics, because always computer is what they are accepting discrete object, not a continuum kind of thing. So that's where discretization is very much important. And in math 2 I hope that definitely you might have already understood those discretization concept. So that one is very much essential kind of things. So I will first talk about outline of this lecture. First I would like to give a recap of conditional probability mass function. That one problem I will talk about, where what we do, we can calculate joint probability with the help of conditional probability and prior probability. So that concept I will talk about. Various time I had already told that it is very difficult to calculate joint probability of any joint random variable. That means if you are having two random variable x and y, then it is very hard to calculate. So what is the approach to calculate joint probability mass function of joint random variable x and y? So we apply the multiplication rule. Through that we can calculate joint probability mass function. So it depends upon your approach, what you want to observe first. So definitely it is a sequential approach to calculate joint probability of two random variable x and y. So sequential, that means suppose someone is observing y x first, then that means observing means that person is having idea of what is the probability mass function of x, and afterward once that person has already observed x, after that he is observing y conditioned on x. So that's why you are having conditional probability mass function of y given x. And if you multiply these two from multiplication rule, then it is giving joint probability mass function of x and y. So this is the approach, and I will take one problem to understand this further. After that I will talk about conditional expectation. So what is happening, that till now expectation is talking about representation of several observed value of the random variable. That means expectation of a random variable, it is a fixed number, it is a fixed number, single number, or representation it is giving. But if you define conditional expectation that with respect to, with the help of conditional probability mass function, then what will happen, that would be what, that would be again a random variable. So we will see a expectation, conditional expectation like this way, expectation of x given y. So it would be a function of y, observed value of y, and hence it would be a random variable, or simply we can say that it would be a function of y, random variable y, because you put conditioning over y. So that's way, if someone is saying that we want to put conditioning over x, then it would be what, y given x, it would be a function of x. So those things we will see it, it is not a difficult concept, we will see it. So it would be a function of x. So I had already mentioned that if you are having a random variable and further you are defining function of those random variable, those again become random variables, and hence we can say that conditional expectation would be a random variable. And after that I will talk about little bit independency of any two discrete random variable. And In later class, I will discuss about conditional variance and various other form of independency like conditional independency and various other pairwise independency and other kind of thing will come. So for coming to first part, that recap of conditional probability mass function in order to calculate joint probability mass function. So here how we calculate? So the conditional probability mass function is often convenient for calculation of joint probability mass function using the sequential approach. How? We can see it like this here. So suppose we are having two random variable x and y associated with the same what we call it a random experiment. So in that case, if you try to calculate joint probability mass function, joint activity, definitely that means it would be very difficult to calculate. So what we do, we can go for sequential approach. Suppose someone is coming and someone is observing y first, happening of y, occurrence of y first. That means you are having idea of the probability mass function of y. That's simply you can say that it is marginal probability mass function or simply probability mass function, both are same. And afterward, what you do, you try to observe x. So that's why for each observed value of y, you are putting a condition over that, and hence we are getting a conditional random variable x given y for that specific value of y. Okay, so with respect to that, you can define a conditional probability mass function that would be x given y. It is defined x given y. Okay, if you multiply these two, it will give joint probability mass function due to that multiplication rule. And if someone is willing to see the derivation is directly coming from the multiplication rule. Further, if someone is willing to observe x first, then this approach will come. Here, what we are observing y first. Here in the second definition of the joint probability mass function, we are observing x first. So that is there. But in the both way, it depends upon problem. Sometimes observation of x would be very simpler. Sometimes observation of y would be very simpler. So depends upon which one is simpler one. Just proceed with that. So here I will take one question. Question is like this way. Professor may be right. Uh, often has her fact wrong and answer each of her students question incorrectly with probability 1 by 4. So that means professor may be right. Professor Wright is asking a certain number of questions, and uh, she commit mistake while answering those questions. What is that probability? What is that probability of committing mistake? 1 by 4, and that committing mistake is independent of other question. That okay. So in each lecture, Professor May is asking, either she will ask one question or two question or one question, two question or zero question, and all these are equally likely. All three kind of that means three type of question equally, either zero question or one question or two question. That means she may ask with ask zero question with probability 1 by 3. She may ask one question with probability 1 by 3. She may ask two question with probability 1 by 3. So that is the situation. Okay, so we have to calculate here the joint probability of these answering wrong question or asking the number of questions. So for that perspective, we need to introduce it random variable. So suppose x is talking about the number of question may is asked. Okay, x is talking about number of question may ask. So x will take what kind of value? X will take either 0 or 1 or 2. That means professor may ask 0 question or 1 question or two question, and easily we can see that the probability mass function for this one is already given here. So what is the probability mass function for this? Equally likely situation is here. So for each value of x, it is probability mass function is uniform discrete probability mass function. That one is 1 by 3. So x is uniform discrete random variable. So very easy to calculate. Tell me, what about y? How we can calculate what are the possible value of y? Anyone who would say y is talking about see the number of questions she answer wrong. The number of questions she answer wrong. So that is. So tell me, what are the possible value of y? If x is taking these three type of values, 0, 1, 2. Yeah, very nice. So yeah, 0, 1, 2. So maximum wrong answer it might be 2 associated with this. When x equal to 2, then you will get it. So y is taking this one. Now tell me, can you find the probability mass function of y? What is the probability mass function of y? Anyone? Can you find it? Here, just remember that this probability is 1 by 4. It is what? Answering incorrect. No, it is not like that. Uh, Actually, it is very difficult to calculate right now. Simply, if you calculate here, conditional probability is given. Yeah, yes. Here, listen here. Conditional probability you can calculate. That means x you have already observed. Then you can calculate. Sorry, y given x. Conditional probability mass function of y, not y. You can't calculate probability mass function of y directly. You can able to calculate probability mass function of y given x. That you can calculate from this problem. This you can calculate, but I'm asking to calculate this one, it will take time. Directly you can't calculate. So you can calculate this thing. Did you get the meaning of this? Because regarding x, everything is clear. We don't face any problem. Probability mass function is already given here from the question. It is so that's why x very fine to proceed x first. Observation of x first. After that, try to observe x. So this is here compatible. You can compute. Definitely, the probability mass function of y is also compatible, but that is little bit difficult. But this one is easy. So in next slide, I will talk about how to compute. Okay, so this joint probability mass function here, our intention is to calculate joint probability mass function that can be constructed as follows. That means that distribution of x is very easy to observe. So we are observing x first. So joint probability mass function of x and y, we can compute it as a product of probability mass function of x into probability mass function of y given x. For example, just we observe one question is being asked and one wrong question. That means x is talking about one question, be x value x. This one is x1 is taking, x is taking 1 and y is also taking 1. So y is taking 1. So if I'm asking what is the probability of y equal to 1, that would be difficult to calculate, but we can calculate probability of y given x1. That would be easy to calculate. This would be easy to calculate, but if simply I'm asking what is the probability of y equal to 1, that would be little bit difficult. So how we calculate it? So we can calculate like this way. That means here x equal to 1, y equal to 1. So we are applying multiplication rule, that probability that x is taking value equal to 1. Afterward, probability that y is taking value 1 given x equal to 1. So this one is the conditional probability. And what is the probability of x equal to 1? And that one is uniform distribution. So probability is 1 by 3. And if one question has been asked, then what is the probability that that question would be wrong? The probability of being wrong answer, what is given? That one is 1 by 4. 1 by 4. Probability of being so when you come to say that one answer would be wrong, when that professor may will ask one question, then there is a possibility of answering wrong answer. If professor may is asking zero question, then how the existence of value of y equal to 1 is not possible. So it is highly dependent, conditional approach. Are you getting the meaning of conditioning? Suppose professor may is asking zero question, then is there a possibility of getting wrong answer from professor may? Is it possible to get y equal to n? One wrong answer from professor may? Is it possible? Anyone? No possible. not possible. So simply it is not possible. That's why it is highly dependent on x. So you need to observe x, then you can talk about observation of y. So that's why you can calculate conditional probability mass function. So we are calculating here conditional probability mass function. So just multiply all these. So probability of 1 it would be what, 1 by 12 simplified. Now another situation I am taking it here. Suppose x equal to, again Professor May was asking one question: what is the probability that Professor May is answering zero wrong, is giving zero wrong answer, zero wrong answer. If asking one question, zero wrong answer. So that means this will come directly. Yes, zero wrong answer means answer was correct. Zero wrong answer means answer was correct. No wrong question. No, sorry, no wrong answer. Correct answer. Zero means no wrong answer. What is meaning of no wrong answer? That means correct answer. Did you get? So that's why y equal to 0. So we need to give a legitimate random variable. So that's why these are numeric approach. So anyhow you have to adjust with that problem. Okay. So y equal to 0, that means y is counting number of wrong answer. And y equal to 0 means there is no wrong answer. That means there is a correct answer. So professor may ask one question and answer correctly. So that event we try to calculate it. So for the probability that, so for that we know that probability of answering wrong, giving wrong answer is 1 by 4. So what is the probability of giving right answer? That would be what, 3 by 4. That would be 3 by 4, and hence we are calculating probability of 1 0, that event 1 0, it would be 1 by 3 into 3 by 4. That means probability of giving in one question, probability of giving right answer would be what, 3 by, if you are asking one question, that means joint I'm talking about joint occurrence of these two, x equal to 1, y equal to 0. So that probability would be 3 by 12. So likewise we can calculate how many, so how many that joint value of x and y we will observe here. X is taking how many value? X is taking 3 value: 0, 1, 2. Similarly y will take 3 possible value. So in total if you try to make it like it is a if you are talking about joint value, so it is always talking two dimensional. So x is taking two value, three values, so 0, 1, 2. Y is taking also three value. This point is 0, 0, 1, 2. Okay, so in total how many value you will get? That how many order pair you will get? What is the order pair? This is, it is just simple counting principle. How many order pair you will get? With 3x, 3 value of x and 3 value of y, how many order pair you will get in total? 8. Just count all these boxes. I'm making all this thing. So 0, I'm raising it. It is difficult to. Okay, see it all this, count it here. So how many boxes you are seeing? A 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 into 3, 9. 9 pair would be there. It is simple multiplication rule. 3 value for x and 3 value for y. 3 into 3, 9. 9 pair you will get. That is the. It is not like that I am asking to fill 2 box only. So 9 in total, 9 pair you will get. Now we will try to calculate probability of each pair. Each pair. So we do it sequential manner. So first I told that the observation of x is very simpler. So we are observing first. So x is taking 0 value, 1 value, 2 value with equal probability 1 by 3, 1 by 1 by 3. Suppose x is observing 0 value. With respect to that, there is no value for y. y won't take, because x is observing 0 means professor may is asking 0 question. If that was professor is asking 0 question, then there is no meaning of to give right or wrong answer. It would terminate. Now when professor may is asking one question, then there is a possibility that the professor may answer one wrong question or 0 wrong question. So two possibility are coming. So one wrong question with probability 1 by the professor may will answer one answer wrong wrongly with probability 1 by 4, and answer rightly with probability 3 by 4. But if suppose professor may is asking two questions, in that case professor may uh, answer wrongly, that is zero wrong answer with probability 9 by 16, one wrong answer with probability 6 by 16, two wrong answers. What here you are talking about this one, this will first one, this. Okay, this second, that when y is taking 1 and given that x equal to 2 here, this conditional event, so it is very easy to calculate. That means how you observe that. So one wrong answer, what is the probability of so if you try to observe this event, this conditional event, what was the probability of wrong answer? 1 by 4. And what was the probability of here 3 by 16. Like just calculate this one. So it is talking about 0. So here two scenario will come. The order is also matter here. Two scenario will come here. Simply you can calculate 3 by this is 3 by 4, both here 0. Two question has been asked, so that means 3 by 4 into 3 by 4, both question his answer was wrongly he answered. Sorry, rightly he answer, both question rightly he answer. Y equal to 0, that means there is no wrong answer, both are right answer, 3 by 3. So okay, if you are coming for the either first one or second one, so that's why you have to multiply with 2 as well. Okay, 2 times 3 by 16. It is just binomial random variable kind of things. Okay, or similarly you can get it 1 by 16. So okay, so this is for second layer, that for a number of question answer wrongly. So okay, and now the leaf, it will talk about joint occurrence of x and y. So all these, so how many you can count it, total 9 leaf you will observe. So all those value you can put it here. So in this tabular, this is the tabular form. So tabular form is the simplified form of the value of joint property mass function. So through this that multiplication rule, you come across to get this value. And this 48 is coming just for normalization purpose. You need to normalize it, make denominator same. So that's why you are coming. Now if I reverse question, that suppose this table is given here, and easily you can calculate marginal probability mass function, conditional probability mass function, everything you can calculate from that table. But to get this table, that one is very difficult task. You need to apply some kind of technique, that sequential approach or multiplication rule, in order to get it. But if I'm asking, I'm reversing the question, that find from here what, just take as a homework, that one is a very simple kind of things. From this table, find marginal probability mass function of x, marginal probability mass function of y. The technique I had already discussed, how to calculate. Then calculate marginal conditional probability mass function of x given y. Now here your question would be very simpler, because you come across to see joint probability mass function. After that you can calculate by marginalization probability, what is the probability mass function of y. You can calculate it here, but directly you can't calculate probability mass function for y from the question itself. First calculate joint probability mass function, and from there marginalize it and get the probability mass function of y. Also you can get probability mass function of x given y, and probability mass function of y given x is already given, we have already calculated. So you do all calculate all these probabilities mass function. It is a homework. You calculate first this one. This one is already very simplest. This one is relatively tougher. This one is also. Third one is little bit tougher, and fourth one is that we have already calculated. Fourth one we have already calculated. So you can calculate all these. So this is end of probability, conditional probability mass function. Now we will talk about conditional expectation. So what is conditional expectation? So I told that it is a random variable. Actually, it is a function of random variable. So that's why it would be a random variable. So we define like this way. Consider two random variable x and y in the same experiment. Then the conditional expectation of x, we condition on y. It can be defined as like this way. Conditional expectation of f for each. So I would like to write it here. For each y, each observed value of y, for each y, observed value of y, we are defining conditional expectation as expectation of x with conditional probability. It is expectation of x, actually expectation of x, but we are taking in place of probability mass function of x, we are taking conditional probability mass function of x. Here we see for each y, that means we have already observed y, and based on that we try to infer about x. So that's why we come across to see this conditional probability mass function of x. So if you find conditional expectation like this way by using conditional probability mass function, then the corresponding expectation we are calling it conditional probability conditional expectation. And what we observe for each y, we are calculating this expectation, and hence what would be, so this conditional expectation, it would be a function of y. It is totally dependent on y. So this conditional expectation would be a function of y. For each y we are getting definitely y is not exhausted given y, so definitely that's why conditional expectation would be a function of y. And here for each y we are defining, and hence what it does, it is like this way, that is for each observed y we are getting conditional expectation as a function of y. Some function of y you will get it after solving it. Y will be there, remain, it is not going to change. Okay, it is not going to exhaust. We take summation with respect to x only, so x will be exhausted, x will be completely overused, used. Okay, y will be there. So that's way for each observed y, conditional expectation of x given y, it would be function of y, and hence conditional expectation defines a random variable, or simply case we can say that as a function of random variable as follows. We talk it g of capital Y. Random variable we always denote it by capital Y, capital letter. So that's where g of y equal to expectation of x given y. Expectation of x given y. For each observed value of y, we are defining conditional expectation. So we have to observe all the value of y in order to that for each all those value of y, we are getting a random variable. That random variable through this conditional approach, we are calling this one a conditional random variable, or conditional expectation as a random variable. This one is a conditional expectation as a random variable we are defining. So if we are having a random variable, then we can talk about two things, two important things. One is expectation of that random variable and variance of that random variable. So if you try to find expectation of this conditional expectation, that would be the expectation of x itself, and hence we will get a law of expectation, what we are calling it law of iterated expectation. So before going to that, I will take one example as well. Okay, so I will talk about law of expectation. So taking out what is known. So known to. So one more thing also we can see it here in the law of expectation. In expected rule, we can easily see in if suppose we are having a random variable x, and we know we are defining a known function of this random variable g of x. Okay, so we are here observing x only, we are not giving observing y, we are observing x only. So that's why condition you can observe it here like this way. Condition given x, that means we are observing x, we are having partial information, that information is talking about x, occurrence of x. So that's way, if you're trying to calculate a probability expectation of product g of x and h of y, and we are observing x first, then we can take out g of x out of the expectation, and it would be just conditional expectation of h of y given x. So this is the very simple kind of derivation. If you go in the definition from the definition of expectation, easily you can get it like this way. For each x, but because x we are observing first, for each x we can define conditional expectation. This is the conditional expectation. Definitely it is function of x. This one is also function of y. So in total it is a function of x, y, you can say it, and we put conditioning through x equal to x, that we are observing x first. So for each x, what will be, this would be just function of x. So we have taken that x, so it is behaving constant with respect to this expectation calculation computation. So you can take it out of the expectation, because this constant is always what unaffected by expectation. Okay, so you can take it out. So we are taking it out, and remaining just we need to calculate. We don't know about y of the observer, we haven't seen observe y, so that's why y would be inside the expectation. And what is that, this will give just conditional expectation of h of y given x, and for each x we are doing. So in that process we are getting this rule, we have to vary for all x. So in that process we are getting this rule. So that's why a small x will be converted into capital X when you are taking all observed value of x, then it becomes a random variable. Another law, it is talking about law of expectation. That means we need to verify. So we had already seen that conditional expectation as a random variable. That means this one, conditional expectation x given y, it is a random variable. Then definitely it will have a expectation or mean, or also it will have a variance. So if you right now, if you try to find expectation of this one, then expectation of this conditional expectation, it would be the expectation of the x itself. This we are calling it law of iterated expectation. So how we can calculate it? Formula is very much simple. So you can proceed in reverse direction. That means first define the expectation of x. So how we define expectation of x? It is summation of the value of observed value of random variable with product, do product with the corresponding probability, corresponding x into px. Simply I would like to say that, and sum over all the value of x. Now what we do, we know that we can get this yes, which one, this here, here I'm okay. You're actually, I think uh, uh, it is very simple. It is just go to definition. For here, this you have to establish. Result say that this is the result. You have to prove that. It is saying that you are taking two random variable x and y. After that, you are defining function of a random variable x, and you are defining function of another function of random variable y. And what is happening that here x you are observing first, x you are observing, you are able to observe x. Okay, that means you are observing, you are putting condition on x, condition on x. So after defining these two functions g of x and h of y, you are defining a new function that is product of these two functions, h of g of x into h of y. Okay, so we'll find expectation of this new, again it would be a random variable. So we'll find the expectation of this one once we are observing x. So we'll find expectation of this one. This is the question. So expectation of this product g of x into h of y given x, how we can calculate? It is just equal to g of x into expectation of h of y given x. So how we can calculate? So here x you have already observed. So for each x we will proceed. For each x, here that for each x, that means you are going case wise x scenario, several scenario of x. So for one scenario of x, g of x definitely it would be fixed constant number. So you can take it out from the expectation because it is a number. You have fixed the scenario. That means x will take x is a discrete value, it will take discrete value in fashion. So it would be g of x would be what, it is a number. So this number it will come out of the expectation. Why? Because expectation we are taking with respect to here, it is coming here x is fixed. So we are not taking expectation with respect to x, we are taking expectation with respect to y only. Why? Because we don't have control over y, we have to take all the value of y, we are not putting any observation over y, we are putting just observation over x. That's where this g of x is coming out. And inside the expectation we are having y, h of y. And you know that, recall the definition of expectation, simple definition if I would like to write it. If I am calling it expectation of y, then how you calculate? Always this one is, consider this one is argument, so it is defined as summation y one observed value of y into corresponding probability mass function p of y, and we have to sum for all value of y. So this is the, so here we do summation with respect to all y. That's way here we have to, once you are fixing x is a constant, then that's way we here this expectation is actually function of y, it is taking summation with respect to y. So we can't take out h of y, h of y will be inside, because but x has been liberated, so we can take it out from this expectation, it is coming out. I think it might be clear, just do practice a lot and then it is very simple result. Okay, fine. So I will talk next one, that the law of expectation. So I told that expectation of x given y, it is a random variable, it is defined with the help of conditional probability mass function. Now if it is a random variable, then surely you will ask another question, is that if it is a random variable, what is the expectation and what is the variance? Automatic question will come. So if expectation of expectation, conditional expectation is what, the expectation of the random variable x itself. So this is giving a what, equality, or you can identity, we can say that. So this we are calling it law of iterated expectation. So iteration you can observe, iteration you can observe that, that's where law so if you want to prove it, so proof is very simple, you go in reverse way. So what you do, proceed with definition of expectation of x. So we can write expectation of x like this way. So now here this marginal probability mass function is coming, and we know that marginal probability mass function, how it is coming, we get this by marginalizing the joint probability mass function of x and y, because here two random variables are coming, so we have to marginalize it with respect to y in order to get marginal probability mass function of x. So we are marginalizing with respect to y, then you will get marginal probability mass function p of x. Now what you do here, in previous slide I explained that how we can get this joint probability mass function. This you can get it just applying conditional problem, that multiplication rule. So that's way I have written this one like this way. So that means here we are observing y first, then observing x, then we are finding. So that's why I have written like this way. Okay, and it is just one kind of manipulation, just you can do manipulation. And what is happening that this you can interchange this summation. This summation is talking with respect to x, this summation is talking with respect to y. So that interchangeable is feasible, it is not, there is no issue. So when we interchanging, so that summation with respect to y, it is coming out. So you can relate it with for continuous random variable, it would be just integral change of actually it is very much easy to visualize change of order of integration in case of uh, double integration. So it is one kind of double integration. You can recall that there is a book by Thomas and Finney, and that book has explained beautifully the change of order of integration. So it is all about change of order of summation or change of order of integration. It is that problem, I would like to say that. So I do the same kind of thing, so there would be no issue in overall calculation. So here we perform that change of order of summation, and with respect to that, what we do, if you try to look into this, what does it talk about? It is talking about conditional expectation of x given y, this one. And here what is that? Simply you can say that it is function of, it would be definitely function of y, y g of, in short we will write it g of y. And if you go further, so we are writing like this way, conditional expectation of y this summation I am talking about, conditional expectation of y into corresponding probability, that probability of y. So what does it is, just what expected rule. It is the definition of expected rule. That means we are taking g of y and we are multiplying with corresponding probability mass function of y. So that one is the expected rule. And from the expected rule we will come across to see that it is talking about expectation of g of y, or that means expectation of conditional expectation of x given y. Conditional expectation of g of y is what? Conditional expectation of x given y. So that's way we started from expectation of x and finally we turn into expectation of x given y. So this law we are calling it a law iterated expectation. Very easy to proceed with. And also if you want to visualize further, there are many other applications you can upload, also related with law of total probability as well. From outcome perspective, if you want to see, I will take one example. After that I will explain few more things. So consider two random variable x and y with joint probability mass function. uh, Definitely it would be, it is already given in table, you can see it like this way. And we are defining a this one is exercise or example one, we can say that. So we are defining a conditional expectation x given y, and we are name, definitely it is a random variable, so we are giving a name to this random variable z equal to expectation of x given y. Then we have to find few question, and what is the joint probability mass function. It is all for x and y, it is given like this way. This is the joint probability mass function of x given y. If joint probability mass function is given, that means you are having information about everything. That means having information about marginal probability mass function, having information about conditional probability mass function, having information about all the four kind of things you can easily calculate from that table. It easily you can calculate those. That calculation, you know, that fix one row and get what exhaust y will be. If you fixing one row, y will be exhausted, and fix second row, again exhaust y. So what you are, you will get probability of x equal to 0. And likewise if you go along with second row, then you will get probability of x equal to 1. So that is what, so the here you will get a distribution of x. That means you will get probability mass function of x, your probability mass function of x. What is that? So if you sum it up, so if you summing, then this value for all y's, what you will get 3 by for x equal to 0 probability, what is the distribution? 3 by 5. For x equal to 1, what would be distribution? 2 by 5. And whether it satisfy a normalizing condition, definitely if you sum 3 by 5 with 2 by 5, sum will be 1. So that probability, it is a legitimate probability mass function, that of x. If you similarly if you do column wise, then what you will sum it, then what it would be 3 by 5. That will talk about probability of y equal to 0. That means value of the probability mass function of y, that one is taking 0 for y equal to 0, and for y equal to 1 it would be 2 by 5. So easily you can 2 by 5 you are getting. So from here you can claim that what kind of random variable x is, what kind of random variable x is, because you know certain number of what we call it discrete random variable, several special discrete random variable. I had already told that. So tell me the nature of random variable x and nature of random variable y. That means question is coming like this one. So we have to find the probability mass function of x, we have to find the probability mass function of y as well, x and y both. Then we have to find the conditional probability mass function of x given y, and okay, also we have to find the expectation of z, and we have to find the probability mass function of z, that conditional expectation. Okay, now I'm asking one question. Tell me what kind of random variable x would be. Anyone would like to comment? X is taking how many value? Just two value. By default, if something is taking two value, you can categorize as Bernoulli random variable. Y is taking how many value? Two random value, two value. So that's y is also a Bernoulli random variable. So you can say it like this way: x and y both are Bernoulli random variable. And then question is coming: what is the probability of success? Probability of success is 2 by 5 for each case. Now, similarly, you can calculate conditional probability for y. If you are taking y equal to 0, then x given 0, it would be again a Bernoulli random variable with probability of success 2 by 5. And you can calculate other conditional probability, what in the question it is given. So you can calculate all the conditional probability, mass function. Now the next question is coming, that how we can calculate probability mass function of z, that z conditional expectation of x given y. So it is already given here. It is very simple to calculate all these expectation, and here try to identify what is the probability, and in that perspective this is the probability mass function of conditional probability. Because this one is what, it is a random variable, so we need to find probability mass function, we need to find expectation, and expectation is 2 by 5. Easily you can calculate by using this probability mass function. If you are able to calculate this probability mass function, you can calculate expectation of z, and once you are calculating expectation of z, then don't directly go to calculate variance of this one. What if you are willing to calculate variance of z, what you do, calculate second moment. This is the second moment, that one is also very easy to calculate, and apply the formula of variance as a difference of first second moment. How we will calculate this one is the second moment, that means expectation of z square minus a square of the first moment. First moment is the mean or expectation. So apply this one, both I have already calculated it here. So apply there and you will get the value of variance of z. So everything, that expectation of z and variance of z, both you can calculate, because this conditional expectation is a legitimate random variable, so you can calculate all those related parameters. Okay, it is already I think above 45 minutes. So other things we'll cover in next class. Regarding attendance, just go and